All right, this is my house. For those of you guys who have taken the Amber book or been part of the Young Architect summer series, you've seen this house. But for the rest of you, I'll show it to you briefly. It's just kind of the culmination. This addition here is the culmination of about 10 years of research into trying to see if we could get simultaneous thermal resistance, basically insulative value insulation, and still allow daylight in. And so what the walls of the addition, the dining room, are made of, they're made of bubble wrap. They're made of 5 layers of like an industrial strength bubble wrap. I'm sorry, 4 layers and 5 air spaces. So we're talking about glass, and then an airspace, and then bubble wrap, and then an airspace, and then bubble wrap, and then an airspace, and then bubble wrap, and then an airspace and glass. And the thermal resistance of that, well, we'll talk about that in a little bit. We're going to calculate that. But this is the inside. It's got kind of a luminous quality. It has doors for view, but the walls themselves are used for daylight. And these are some bubble wrap, less industrial bubble wrap that I put outside and in the sun for about 2.5 years. Actually, one was inside the window and one was outside the window, just to kind of see how it would yellow or pop or furl, what would happen if moisture got in, and so forth. And then these are a model I did of it at the beginning, and then these are some of the models. A lot of them broke, but I'm a big model person. I design with model, and frankly, that's kind of how I teach with my students as well. So these are some of the models that were used to kind of figure out the house and the bubble wrap renovation. And this is it on the outside. So we're looking at a 50% frit, and a frit, of course, is a ceramic paint on glass. That shade, it's a west-facing room, so that shades the bubble wrap assembly from behind, or the bubble wrap assembly that's up behind, and you can kind of see that in here. That's all bubble wrap back there. All right, so that bubble wrap sandwich panel. So here we have the the bubble wrap room, the dining room, and then there's other ways of kind of bringing light in. It's a gut renovation, especially of the first floor and parts of the second floor, to get light into the first floor, because daylighting a space is really all about bringing light deep into the space. It's not about how much light you bring in, it's about how deep you bring in the light. And so there are these skylights here and here that come down to the living room and to the kitchen. And then here's Martin kind of working with the bubble wrap, and it's going to be hung. And you see it hung there and there and there. And here it is from inside when it's done. And again, here's one of the skylights. I got an email by coincidence yesterday asking me if that cat is dead. And the cat died about a week later, but the cat was not dead at that time. That would be morbid. There's also, you see a little lip here and a track. There's an insect screen that comes down on a motorized track that comes down, so we can open up these big pivot doors and kind of treat it like a 2.5 season outdoor room. And here's that skylight bringing light deep into the space in the kitchen. Here's the light coming from the bubble wrap room in. And then here's my cabinetry and a steel pass-through and a island that kind of is on wheels, so it can be moved to this garage right over here. So here it is looking the other direction. And again, you see the skylight. There's my son doing some cutting on that wheelbarrow kitchen island. And there's me. There's a fire pit outside. You might have noticed the scupper here that takes the water from the roof and kind of brings it outboard of the glass, and then it drops it into this steel grate, and then it goes underground. where there's a perforated pipe and gravel that brings it out to another place in the yard. And then that kind of language comes up, and that steel grate becomes then the surface of the tabletop, because I can't stand wiping down a tabletop every time I want to eat outside, because I wind up never doing it. So by using steel grate, I don't have to really worry about that. And there's Vitruvian Man, and there's me doing my best Vitruvian Man. It's got this great glowing quality and light in that room. And then there's, of course, Corbu Man, and it's me doing Corbu's Modular Man. And again, you see the house. So here we are kind of looking at that space. That's really what we're trying to figure out. So the first task is we say, okay, we're given that bubble wrap has an R value of 1.7 per layer, that the wall is 4 layers of bubble wrap and 5 air spaces, and each air space is a ½ inch. And there's 2 1/4 inch pieces of glass on either side of that. And we're going to use 19 degrees as our outdoor design wintertime temperature for Roanoke. That's the nearest major airport, if you can call it a major airport. There are 6 gates, and getting parking right in front of the entrance to the airport is about as difficult as doing so in a strip mall. You can just kind of pull up and go in, so it's a small airport. The wall is 375 square feet, and you can use Google to fill in gaps of information not given. So I gave you the more difficult things to find because you don't know what the R value of that bubble wrap is. But for things like airspace or glass, I said, go ahead and use the internet to try to find it out. And so we're also given this formula, and this is a formula that frankly, architects typically do not have much problem understanding once they understand it. So if you've been studying for this for a while, or if you remember it from school, this is going to be pretty easy. If you haven't, rest assured, it's still going to be pretty easy. You just have to kind of get your head around it. I'm going to go through this formula like 3 times, right? Each with a different kind of aim. So the first time is just to read it. That Q, the heat loss in BTUs per hour, is equal to U, which is the U value of the assembly, times A, which is the area, times delta T. Now, anytime you're given a formula like that, it's really important not to see it just as numbers or as symbols. They're actually real things. So what are we talking about? Well, if we think of our building as a bucket, and the bucket has a hole in it, and we have water in the hole, that's our heat. And water in the bucket, that's our heat. And there's always kind of water spilling out of the hole. And so we're always losing heat in the winter because it's colder outside than inside, and heat kind of finds an equilibrium the way that water does. And so what we're going to need to do eventually is we're going to need to pour heat into the building with mechanical means like a boiler. And we're going to have to pour that in to replace exactly what's going out at about the same rate so that we can keep it warmer inside than outside. But right now we're trying to basically size the hole. That's what the job of this is. And the hole, then we measure the hole in BTUs per hour. Now, BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. So if we're talking about BTUs per hour, we're talking about thousands or tens of thousands or hundreds of thousands or millions, depending on how big of a building or room we're talking about. BTUs, that's a unit of energy per hour. That's a rate of heat loss of unit of energy. Now, we could also talk about heat gain in the summer, but that's a slightly more sophisticated formula, and one that's not really as heavily referenced, not really referenced at all, actually, in figuring out total heat gain. Heat loss through this is the conduction. This does not include heat loss through like cracks around the pivot doors I showed you. It's not air getting out and air getting in. It's actually the bubble wrap assembly heating up from the inside and cooling off on the outside. So we can think of it as the cold kind of working its way in by first the cold will make the outside glass cold, if this is the outside glass and it's 0 degrees outside, or let's make it realistic, 19 degrees outside, that's what we're given. And so it's going to make that glass cold. And then that glass is going to make the airspace next to it cold. And that's going to make the bubble wrap cold, and that's going to make the airspace next to it cold, and that's going to make the bubble wrap next to it cold, and so forth, all the way to the inside. So we're talking about just like the rate of conductive heat loss. Now, in reality, of course, there's convection at each of these air spaces because there's air, and convection is heat exchange through a fluid, and a fluid is a gas or a liquid. And so it's a little bit different when we're talking about air, but what we're going to do is we're going to figure out the conductive equivalence, kind of like an approximation of what the R value of an airspace of air would be if we were measuring it as conduction, and assuming that this whole assembly, including the air spaces, were a solid. We're a solid. All right. So that's the second way we're going to look at it, that we're measuring heat loss. And we want to figure out, how do we measure heat loss? How do we measure the rate of heat, the rate at which heat is going to leave our building? And so there are really three things that go into it, right? The first is how conductive is the skin? So that's the U value of the assembly. So if we make the skin twice as conductive, if we have, for instance, instead of 4 layers of bubble wrap and 2 layers of glass, we had theoretically 2 layers of bubble wrap and 1 layer of glass, so we only had half a wall, our U value would double. It would be twice as conductive. And you can see from the formula, if we double this, then we're going to double this. So it's really important to be able to make those connections, both from an understanding point of view and from a remembering point of view, and from a kind of being able to see a question that you haven't dealt with point of view. This could be asked any number of ways. We could start by giving you the heat loss in BTUs per hour, and the U value and the area, and you tell us a delta T. So it's not always quite exactly going to be in this format. So the more you can be in a position where you understand it, the happier you'll be. All right. So now we have the area. What does that mean? Well, that's not the floor area, that's the skin area of the building. So the skin of the building is a given number of square feet, and this is all in imperial, so it's all in square feet and degrees Fahrenheit and so forth. And what does that mean? Well, that means if we double the area, if we somehow had the same volume of room but doubled the skin area, then we would lose twice as much heat for the same volume of room. And if we halved the area, if we somehow made a more compact form of our building, this is not talked about that much. We're always talking about R values and kind of BTUs per square foot of floor area. But if you have a compact form of your building, if you have a building that looks like this in plan or section versus like, an airport that looks like this, something like that, for the same volume of building, you're going to have a good deal less heat loss coming through here than you have coming through here. All right. And finally, we have delta T. And delta T is the difference in temperature, the difference in temperature between inside and outside. So if instead of, if it's going to be 70 degrees inside, the delta T, the difference in temperature from outside to inside, is going to be 70 minus 19 degrees. Now, how can we as architects change that? You might think we can't, because how can we control the temperature outside? And I guess we can't, but there are ways to make it comfortable at a cooler temperature inside. So for instance, this particular bubble wrap room has radiant floor heating, and that allows me to turn down the thermostat inside. So at maybe 65 degrees inside, I'm just as comfortable with an air temperature of 65 because I'm exposed to a warm surface, like almost like a campfire, but not, than I would be at 70. And so that's reducing the difference between 65 and the 19 outside is less than the difference between 70 degrees inside and 19 degrees outside. So that's what delta T is. And again, if you double delta T, if you increase the difference between inside and outside by cranking up the thermostat in the winter or putting it way low in the summer, you have also doubled your heat loss. So again, heat loss is how much is coming out of the bucket. And finally, let's go through it one more time. What we're saying is that heat loss is equal to how crappy the insulation is times how big your skin area is times the difference in temperature between inside and outside. All right, let's get to work. Now, if you Googled it, if you typed in what is the R value of an airspace, you would come up with these numbers. And so let's talk a little bit about what that means. So it says airspace is minimum ½ inch up to 4 inches, and it's 1. And that's a good way to remember it. So an airspace is 1. Now an airspace is when we have something like glass and bubble wrap and then a space between it. An air, more typically in a building, we might have, some kind of in plan, we may have studs, and then we have like maybe a 3.5 inch airspace in between, and that's, again, that's a ½ inch up to 4 inches, and so that's going to be R1. It's not much, but we'll take it. It's worth measuring. It's enough to be worth measuring, but it's not enough to impress anybody. So so now what we have is we have the R value of the airspace. Now, what's this stuff? R value of interior wall, interior ceiling. That's a different thing. And so if we zoom in to that surface, that exterior surface, and we were to zoom in, we would see that that exterior surface is not smooth like that, but it's actually kind of craggy. At the molecular level, it's craggy, it's bumpy. And if we zoomed into one of those bumps, we would see that there are molecules kind of just hanging out in there. And so it's almost like a little air film is being formed, and that air film provides some insulative value. Now, it's not a lot in the winter. It's probably like R equals 0.17 is the number they give. I don't know why they need to be that accurate. It seems silly. To the 100th seems a bit overkill to me, but relative to how accurate the rest of the measurements are. But it's kind of like measuring the distance from me to you in inches. Like, it seems a little bit silly. We'd probably rather measure it in miles. But anyhow, so it's going to be R.17, and the inside on a wall is going to be R value. This is going to be the same thing. There's little microscopic kind of film of air that gets caught up in the craggy surface of the wall. Now, with glass, it's probably not that craggy, but with drywall or something like that, the R value of the interior air film is going to be 0.68 for a wall. They also give 0.61 for a ceiling because heat rises. But again, these are way too detailed, in my opinion, relative to measuring the R value of a building assembly. Now, why is the outside R value less than the inside R value? Go ahead and take 4 seconds and tell that to yourself out loud. The reason is because there's wind outside. So that wind kind of takes those molecules and it blows them away when they get warm. So they don't, it's not kind of the same kind of a barrier, because the barrier is always being blown away and being replaced by new molecules of outdoor air that haven't had the benefit of being warmed by the inside. All right. Now, why does it only go up to 4 inches? Why does it only go up to 4 inches? Well, if we look at our wall here, and here we're looking at it in plan, but let's say we're looking at it in section. So I'll draw it over here in section. So here's our interior finish material. Say it's drywall, just to keep it simple. And we're looking at it in section. And here is our exterior cladding material. And let's say it's kind of crappy siding or something, whatever. And then we have this airspace in between. And so what's going to happen, as you might imagine, is this airspace in between has molecules. And these molecules, if it's 19 degrees outside and it's 70 degrees inside, these molecules are, when they get near this surface here, the outdoor surface, these molecules are going to get cold, because this 19-degree surface is making this siding cold. And so these molecules are going to get cold. And what happens to a fluid when it gets cold? Well, it sinks. So there's going to be a process by which the molecules are going to sink along the outside in the winter of that airspace. And then on the inside of that airspace, the molecules that may be near the inside are going to be warmer relative to the rest of the average in that airspace. So they're going to rise because they're being heated. And then you get what's called a convective loop in the airspace. You get a convective loop in the airspace. And so is it so much that if you stuck, if you drilled a hole and stuck your pinky in it, you'd feel a breeze? No, not even close. But it's enough that if you get this thing going in earnest, it turns your airspace from a net positive to either nothing or maybe even a net negative in terms of keeping heat in. So if your airspace is more than 4 inches, especially like more than 6 inches, then the two sides are far enough apart that the downward stream on the outside, this one here, is out of the way of the upward stream on the inside. And you get this loop going, and it's called a convective loop, and it turns your airspace into either nothing or less than nothing. So 6 inches or more, less than nothing. Now, when you get over 10 inches, it could be, it's a little unclear. I've been looking at the literature and research in that, and it's a little unclear. I think it kind of depends on the specific fluid dynamics of that space, how tall is the airspace and so forth. But when you get above 10, there's some reason to believe it starts to get beneficial again. The airspace starts to get beneficial again. But in that kind of 6 to 10, which is not an unusual thickness for a wall or a ceiling assembly or roof assembly, the airspace actually does you wrong when you're in a wall, not so much a floor ceiling assembly, because the sunken air doesn't quite have the same, it's not going up one side and coming down the other on a ceiling or on a roof. But anyhow, that's what these things are for. In general, I don't know that you need to know that for the exam anymore. Certainly back in the day in ARE 4.0, that was something that was in play. I haven't had a lot of questions on it lately, so I don't know if it's just less important to people or if people are learning it through the Amber book, so they're not asking me or what. But it's worth noting. It's worth noting. All right, that's a convective loop. And that is an air film. Now, it is so easy, even after I just explained it to you, to confuse an air film and an airspace. An airspace is the space in like an enclosed space, like in the cavity within an assembly. An air film is on the surface of the inside and on the surface of the outside. So no matter what the assembly is, we can add 0.17 and 0.68 to it. But again, typically those aren't really, it's not that big a deal for the exam. Now, about 1 in 6 of you right now are saying, but what if it is? What if they ask you? Well, then go ahead and answer it. But if they don't mention it, then you can assume that you don't have to know that 0.68, because truthfully, a good insulative wall is going to be R25 or R35. And so that 0.68 or 0.17 is more or less a rounding error. It's not going to be that big a deal. And the wall R value probably doesn't include some of the thermal bridging that's going on right here. So it always was an approximation anyway. And it's always based on it being 19 degrees outside. But what if it's 21 degrees outside? So it's too fuzzy to be really picky. And what you're going to find, it's not very sexy, but what you're going to find in the end is that insulation is really just about insulation. that's my takeaway. Your insulation is really just about your insulation. So your R value of your brick or your plywood or your OSB or your masonry or your drywall or your airspace or your air film or your concrete block or whatever it is that makes up your assembly. And unfortunately, NCARB's kind of obsessed with the wall, but I would hope that when you're thinking about your projects, you're thinking about your overhead plane as well. But let's just call it the wall. The insulation value, the R value of your wall is still, all that stuff combined is still going to generally be a rounding error compared to the insulative value of the insulation that's in the wall. So once we fill this wall with insulation, then everything else becomes more or less a rounding error. Now, it's important enough to be included. It's not a tiny rounding error, but it's just not that important. All right, let's move on. So we have, if we type in R value of gypsum board, we get 0.45. But if we type in R value of single glass, we get 0.91. Again, that seems a little bit specific to me, but we'll call it 0.9. And where did I get that 19 degrees? Well, at Roanoke Airport, I just searched, outdoor design temperature. It's kind of like 50-year flood elevation. It's kind of like, the not worst case scenario is 19 degrees, but it's, 99% of the time, it's going to be above 19 degrees at Roanoke Airport. What happens if it goes down to 15 degrees? Will our building be able to keep up? No, it won't, but it's not like the whole system fails. If you plan for 19 degrees and instead it's 15 degrees out, well, when you plan for 19, if you plan on 70 degrees inside, then it's going to become 66 degrees, because instead of 19, it's 4 degrees lower. So instead of 70, it'll be 4 degrees lower inside. You'll put on a sweatshirt or you'll plug in an electric heater. It's just not that big a deal. All right. So that's where I got the 19 from. Now, so what we're talking about is we're talking about an R value for the airspace of 1 and an R value of the glass of 0.9. And so what we're asking is how much heat loss through a wall, first with just one layer of glass. So if we have a wall that instead of a bubble wrap assembly, we just have one layer of glass, and we're given that the wall is 375 square feet. That's the total wall area of my bubble wrap assembly, or my bubble wrap room. And so what we're going to do is we're just going to plug these numbers in. And you remember the heat loss, how much is coming out through the bucket, is equal to how crappy the insulation is times the area of the skin times the difference between inside and outside. Now, so I used 375 square feet for the area of the skin because that's what we're given as the wall area. And I used 50 because that's 69 degrees minus 19. It's just a nicer even number, and maybe we're going to set the thermostat inside for 69 instead of 70. We have that power, depending on how accurate we want to be, whether we want to measure in inches or feet or miles. We can kind of do any of these. All right, so now we have to figure out the U value. What is the U value? Because the area is given, and actually so is the difference in temperature kind of between inside and outside if you assume 70 or 69 degrees inside. So what is the area outside? Or sorry, what is the U value of the assembly? Well, we're given, or we figured out by looking online by typing in what is the R value of glass. We have an R value of glass of 0.9, and the U value is 1 over the R. It's the inverse of the R value. So what we're going to do is we're just going to take the inverse of the R value, so that's 1 over R, and 1 over 0.9 is 1.1. So we have a U value of 1.1, and that makes sense because if this is the U value, then this is the R value. And if this is the U value, then this is the R value. As one goes up, the other one goes down. So the R value is like saying, how good is your insulation? So a higher number means you have better insulation. But the U value is like saying, how crappy is your insulation? And that makes sense because if we double the crappiness of the insulation, then we double the heat loss. So we want something that is a number that gets higher when our insulation gets more anemic. And we want a number that gets lower when our insulation gets more robust. So we're going to take this 1.1 and plug it into our U value. And so we wind up with a heat loss in BTUs per hour of 1.1 times 375 square feet times 50 degrees. And that's going to give us our BTUs per hour. And that works out to be about I rounded, about 21,000 BTUs per hour. And that's acceptable to round in this situation. We just kind of have a general, this is kind of the schematic design, maybe the design development stage. We're just trying to figure out like how much will we save if we decide to pursue this bubble wrap idea. All right, now, yeah, there are people out there who are kind of upset that I just didn't really have a units here. And for the rest of you, you can go get a drink of water. But for the people who are upset about no units there, that U value is one of those values you look up in a table and its units make everything else cancel out. So we're trying to go from square feet degrees Fahrenheit to heat loss in BTUs per hour. So it winds up being the units is BTUs. The units of a U value is BTUs per hour, because that's what we want to come up with in the end. And we want to cancel out our square feet. So square feet's going to go on the bottom. and so is degrees Fahrenheit. So that's our unit for a U value. Because when you plug that in, the square feet and degrees go away, and what you wind up with is BTUs per hour. Now, of course, an R value of 0.9, I didn't put a units on there, but it's just the inverse of that. It would just be hours, square feet, degrees Fahrenheit per BTU. So it's one of those nice constants that just kind of converts the area of the building and the difference in temperature between inside and outside to BTU per hour, to a rate of heat loss or heat gain through conduction. All right, now let's see how much goes through the wall when we have the bubble wrap. So now we have this thing where we have the glass, which we figured out was going to be 0.9, an R value of 0.9, and the airspace, which we figured out is an R value of 1, and then the bubble wrap, which we were given, is an R value of 1.7, and then another airspace, which is an R value of 1, and then that second bubble wrap is 1.7, and then airspace of 1, and bubble wrap 1.7, airspace of 1, and bubble wrap 1.7, and then airspace of 1, and then glass. So we have 5 airspaces and 4 layers of bubble wrap and 2 layers of glass in our assembly. So what that actually looks like is, here's the structure of the addition, and here's the bubble wrap, and here is Martin hanging the bubble wrap, or in this case, the glass is there, and then here's the glass, and the bubble wrap is going to hang actually from magnets in layers. So it winds up being kind of a semper, kind of almost, it's almost a fabric. It's almost a woven kind of wall. Anyhow, all right, so now we're going to figure out the heat loss with the bubble wrap wall as an alternative to this single layer of glass. So we still have 375 square feet of glass. It's still our wall area, or of wall. And we still have a delta T of 50. We haven't changed that. And so now we have our U value. What's our U value? Our U value then is going to be, well, let's figure it out. We're going to have to first figure out our R value of each of these elements. We're going to add them together and come up with a total R value for the assembly. Then we're going to take the inverse of the total R value. So you don't take the R value of each element in an assembly and take its inverse. Instead, you add up all the R values first. You add up the glass and the airspaces and the insulation and the bubble wrap and the glass, and you add that all up first. You come up with a total R value. Then the U value is equal to 1 over the total R value, because if you took the inverse of this and added it to the inverse of this and added to the inverse of this, the numbers don't work out. And I can explain later if you're curious. I'll do an example, but trust me, the numbers don't work out. So here we have 4 layers of R1.7 bubble wrap, and we have 5 layers of R1 airspace, and we have 2 layers of R.9 glass. So each of these, as I mentioned, is kind of a rounding error, but you kind of start multiplying them by 4 and 5 and 2, and they add up. So, so what we have is we have an R value of 13.6. Now, someone wrote on the chat, so thickness does not matter. Sure, it does matter, but all of these values were given with an established thickness. So we said that if we look at, we say that the bubble wrap, it already knows it's per layer. So it's not per inch, it's per layer. The airspace we saw between 4 and 10 inches, I'm sorry, between 1/2 inch and 4 inches, it's R1. The glass was 1/4 inch glass. Now, there are some materials, and I'm talking to you, concrete and insulation, that the R value is given often as a resistivity, which is lowercase r. And resistivity, you're going to have to take the resistivity, say the resistivity of insulation is 5, that means it's 5 per inch, R5 per inch. So if we have 6 inches of that type of insulation times R5 per inch, we get an R30. So there are some situations where we have a homogeneous material like cellulose or polystyrene or fiberglass insulation or concrete, where we don't know beforehand exactly how thick the application is going to be for this particular building. but we do know per inch what the R value is going to be, and that's measured in resistivity. Now, the inverse of resistivity is conductivity, and that's given with an lowercase k. So k equals 1 over r, little r, and big R is equal to little r times the depth or the thickness. So you might want to kind of take a screenshot of that and remember that, because that's actually fairly important as well. I'm glad you asked that, person in the chat. All right, so we have a total of 13.6. So we had 1.7 times 4, that's our bubble wrap assembly. 1 times 5, that's our airspaces. 0.9 times 2, that's our glass. And we have a total R value of 13.6. So what do? Do we put the 13.6 in here? No, we have to take the inverse of the 13.6 first. So to make it a U value, and that U value equals 0.07. Now you remember before, our U value is 1.1, and 1.1 looks the same as 0.07, but it's not. 0.17 is less than a tenth of 1.1. When you get in those small numbers, the decimal points can kind of fool you. It's the 0.07 is much less than 1.1. And so when we take that U value for the 0.7 U value of the bubble wrap, and we put that in that formula where we're figuring out how much heat goes out of the bucket is equal to how crappy our insulation is, and now it's not that crappy, times how much skin area we have, because your fingers are colder than your core because they have a lot more skin area exposed to the air, times the difference in temperature between inside and outside, because of course there's going to be a bigger hole in our bucket if it's cold outside. If it's warm outside, or it's just mild outside, there'll be a tiny hole in our bucket. And so when we put that in there, it becomes 0.7. That's how crappy our insulation is, times our area, times our delta T. And we wind up with 1,300 BTUs per hour. Now, as always, don't just look at that as a number. It's really only important, only relevant if you compare it to what was it when we had the full everything was glass. So this is with bubble wrap, 1,300 BTUs per hour. That's our hole, our size of our hole in our bucket. And what's the hole when well, it was a much bigger hole. If you remember, it was 21,000. So we dropped it by 90%. So relative to single layer glass, which of course I probably wouldn't use, that would be irresponsible, but relative to single layer glass, we've eliminated, I don't know, 90% plus of the heat loss. So it seemed like a pretty good idea to do. It seemed like a reason. I did this calculation before I started, and I thought that seems like a reasonable benefit. I can get essentially the insulation of an opaque building, but I can get daylight at the same time. And so what should the insulation be of your building? Well, it kind of depends, of course. It depends on what the use of your building is. It depends on how big your building is, and it depends on the climate your building is in. And it probably depends in no small part on what your goals are. Are your goals to kind of do the minimum possible, or are your goals to do the right thing for all of us and do something about climate change? And so, and it turns out insulation generally is not that expensive. Especially cellulose is pretty cheap. Glass fiber is more expensive. Mineral wool is more expensive than glass fiber. And the petroleum-based foams like polyisocyanurate and XPS and EPS, which are extruded polystyrene and expanded polystyrene respectively, those are more expensive still. So we're going from kind of cheap to more expensive. And that's probably a good topic for another future 40 minutes of competence. But anyhow, I'm going to go ahead and start from the right. So in the black bars are hot climate, and on the y-axis is our recommended thermal resistance. And I just picked, when I made this drawing, I just picked a medium-sized office building. These numbers vary. Depending on the size of your building in large part. But and so in a hot climate, we want R2 windows. That's kind of double pane windows. And in a cold climate, we want R3, and that's double pane thermal break in the frame, and argon starts to approach R3. In our floor, if we have a floor that's like above an unconditioned crawl space, which I don't recommend, but we have a recommendation in a cold climate of R21 and in a hot climate of R10. In a wall, R19 for a cold climate and R8 for a hot climate. In a roof, the more I read about roofs, I think these numbers are a bit low. You could probably double these numbers. Probably if you live in a mixed or cold climate and you're building a building that's not really big, probably the single least expensive, easiest thing you can do to get the biggest bang for your dollar of design time and the biggest bang for your dollar of construction costs is to really thicken up the insulation on the seal in the overhead plane in the roof, the rafters. So anyhow, they recommend R35 for a cold climate, R25 for a warm climate. I would go ahead and double that, or come close to doubling that. Get as much as you can. It will pay for itself many times over, typically. All right, so yeah, we're going to skip that. All right, so your question for next week, and I'll try to send out a higher quality image. I didn't realize how bad this had come, but this is actually, I just took these pictures 5 days ago, on a walk. So snow fell, and you can see on this roof, on this first roof on the left, the snow is melted in between the rafters, but there's snow at the rafters. But at this roof, the snow is melted on the rafters, but there's snow in between the rafters. So what's the difference? That's your question. So we're going to kind of continue thermal. And actually, for those of you guys who are attending the Young Architect Winter Series conference, tomorrow I'm presenting the continuation of what I just showed you. So actually, the spiel I just gave you was what I did at the summer series, the Young Architects Summer Series conference, for those of you guys who were there. For those of you guys who are at the Young Architects Winter Series tomorrow, I'm going to be taking it from here. So in other words, okay, now we know how much heat we lost. How do we size our heater? How do we size our boiler or our heat pump, radiators and our duct sizes and our grills and our registers, and how do we design a system? So the title of the talk tomorrow is How to Not Be Bullied by Your Engineer. And the truth is, it's not that hard to do what they're doing. It's pretty much, I mean, at this level, at the kind of schematic design level, it's pretty much just spreadsheet stuff and formulas like we just looked at. All right, that concludes it for our new content. Let me look over and see what our chat questions were from last time. The first question is, what is the difference between construction manager as agent and construction manager as advisor? All right. I'll show the diagram that Architect's Handbook of Professional Practice loves, and it's actually a pretty good diagram. And frankly, the NCARB folks love it also. So we have the owner, and we have the architect, and we have the contractor. Now, when and this was a topic you can look at last week's. If you weren't there, you can look on the unlisted YouTube channel and view it from last week. But last week we talked about the construction manager. And so the construction manager as advisor is when the owner kind of early on, for reasons of speed and constructability and kind of making sure things that the architect are designing are constructible, and just kind of general advice and cost, kind of saying, you know, cellulose would be a lot cheaper than rigid foam insulation like polyisosanurid here, and it meets the fire code, so let's use cellulose here instead, and we'll save ourselves $40,000. That's the reason you hire a construction manager, and he or she comes on early, and he's just another consultant to the owner. Just advising the owner, working with the architect at the beginning, working with the architect and the contractor as construction goes on. That's as advisor. Now, eventually, one of these construction managers said, you know, owner, you are really, really good at pharmaceutical research and developing vaccines. You really don't need the headaches of having to take your take your executives out of the work, out of the important work of developing vaccines, and instead be worrying about hiring lawyers and debating things with architects and contractors and dealing with all that. Let me take care of that for you. And so that begat the construction manager as agent. So in construction manager as agent, the owner, instead of hiring and having a contract with the architect, the owner hires a construction manager that's going to be a little bit more turnkey. And if you don't know what turnkey means, they're going to take care of everything. Now, of course, they don't take care of everything. The owner is still involved, but the construction manager then is going to deal with the risk that the architect is going to die halfway through the process, or that the contractor is going to get wiped out in the stock market and have to declare bankruptcy. So now it's the headache of the construction manager, because the construction manager is then going to hire the architect and sign a contract with her, and hire the contractor and sign a contract with him, and just deal with all of the paperwork and all of the change orders and all of that stuff, and report back to the owner. So this thing on the right is agent, a construction manager is agent. And this one on the left is construction manager. I'm sorry. This one is advisor. One on the right is construction manager as advisor. The one on the left is construction manager as an agent, because she is going to work as an agent of the owner, and say, I can speak for the owner when I say that change order should not be anywhere near that expensive. And the contractor, because he has a contract with the construction manager, will negotiate the change order with the construction manager, and the owner is kind of left out of it. All right. I still don't understand why no bid in CM as constructor. According to A133, construction management shall develop bidder's interest for the project. Participant answer. Thank you, participant. There are cases that this construction manager as constructor hires multi-prime, then yes, he can go shop for a bid. So the construction manager as constructor, and so in that case, we have the owner, and the owner hires it's where the construction manager gets even more involved. The owner hires the architect, and even maybe before the architect is hired, the owner hires a construction manager who is later going to build the project. And that construction manager then sometimes will issue multiple prime contracts. So they'll say, okay, you do the core, and you are responsible for the shell. So in that case, the construction manager may have multiple prime contracts, and then the core contractor will have lots of subs, and the shell contractor will have lots of subs as well. All right. And that's what multiple prime means. It means there's multiple contractors who are then gonna each be responsible for a portion of the project, and they're all doing the project together, but each of them is doing different work on the project. Maybe one of them is doing, one of them is responsible for the runway, and the other one's responsible for the airport, or one of them is responsible for the fit out of the movie theaters themselves, the actual theaters, but the other one is responsible for the rest of the building, including the exterior and the popcorn stands and lobby. You get the idea. Sometimes there's people who have expertise in runways or movie theaters, and you want them to be the one to do the contracting. And there are other people who have more general expertise in building and are probably less expensive, and you might want them to do the rest of the building, the vanilla part of the building. All right. What contract is used between the owner and construction manager as agent? For CM as advisor, there is C132, but I haven't been able to find one for CM as agent owner. Participant answer, again, thank you, participant. It's also C132. Will the current YouTube videos still be viewable after next week, even without a membership? So last week I told everyone that once we get to our first 40, and I think this is number 39, once we get to our first 40, we're going to stop posting. We're still going to make it, we're still going to make 40 minutes of competence free for anyone who wants to come. So if you want to study with us, come. And we'll still make the old 40 minutes of competence videos available to those who have an Amber Book subscription, but we will not be posting for the public or the unlisted public, because it's an unlisted channel, new 40 minutes of competence videos after next week. Now, the question is, will the first 40 still be viewable? And the answer is yeah. The current YouTube videos, I wouldn't take those down. I'll leave those up. Just new ones are not going to be available. All right. Now is your chance to ask me a question. So let me make it so you can unmute yourselves. You should be able to unmute yourself. Maybe.
Hi, can I
Hey.
ask first question? Why did you say that you don't recommend unconditional crawl space?
Okay. So this was an issue for years, decades. Should we ventilate the crawl space or should we condition it? And so there are two different thought processes. One is that you have a building like this, and you have the ground plane. I exaggerated the size of the crawl space here. And you treat the crawl space like you would a basement, and you insulate and make airtight the whole thing. And the other approach was to say, okay, you have a building in section, and you have an airspace, you have a crawl space, and you have the ground plane. And what we're going to do instead is we're going to put vents in it. You've seen crawl spaces with vents, generally in older buildings. And we're going to ventilate it, and then we're going to use air to keep it dry, and we're going to insulate this, and we're going to do that. Awesome. And then very often, frankly, you had situations where you had some kind of weird hybrid, which should never be done. From the building science, that was always clear, but it wasn't always done. It wasn't always. So you'd have, vented crawl spaces, and you'd have your occupied space above, but then you'd insulate down here. And of course, the air just then goes into your space, or into your, and then the cold down here goes right up in. And the reason that we now pretty much always do this is because this proved to be kind of wet. It's just a moisture problem always. So you would have, there's just an amazing amount of water that comes up from the earth. It just comes up from the earth. The soil is wet, and there's always water coming up. And generally, it was just hard when you had, there almost was never enough air to really dry it out in there. And so you wind up often with condensation or mold or some combination, because you have a dark, damp space that never gets light and maybe doesn't get enough air. Also, generally, you had things like thermal bridging through the structure on the floor, and you had insulation often on the top of the airspace that was fibrous, and so that moisture then, made double mold, because it's fibrous insulation that's always exposed to dampness and darkness in the crawl space, because that insulation I made it look like it was in the building, but usually it's actually underneath. So what we'll essentially do, and what I did here for the crawl space on this building, is you treat this crawl space just like you would a basement, and you insulate it like you would a basement, and you waterproof it like you would a basement, and you make it airtight like you would a basement, and you treat it like it is the continuation of the space. Now, because this is kind of a weird situation, because it's like, once you go down this road, man, once you go down this bubble wrap road, like, it just sucks. Like, everything, every decision, you're like, oh, I didn't think about that. So look at this thermal bridging, man. If it's cold outside, this steel, how do you steel? Because that external frit, I use that external frit because it's facing west. The external frit shaded the building, and not just for thermal reasons, but also kept some of the UV light from breaking down the bubble wrap. I've had that bubble wrap house now for 3.5 years, and there's been no yellowing of the bubble wrap. And that was a lot actually that went into that, but I'm not going to get to that for a second. So so that we needed steel. We needed steel on the, we needed steel to hold up the frit. We needed the frit to keep it from yellowing and to keep it from overheating and keep it from melting and everything else. The steel couldn't touch the foundation, or the steel from the frit couldn't touch the foundation because I'm an obnoxious architect and I really, really, really wanted that corner to float. I just wanted that corner to float. It was like, I can't describe it. It was completely irrational, but it just, every model I made, it just did not work as well compositionally when that corner went down to the earth. It needed to float. So we have this cantilever situation. We have a cantilever situation, we need steel. We have steel, now we have a cantilever steel, so we have thermal bridging. So we have the steel, which gets cold because all of this steel is on the outside of the envelope, because I'll show you. You can kind of see it here. The steel is inboard of the frit, inboard of the screen, but outboard of the actual bubble wrap. You can see it, you can kind of see it right in here. Well, you can see it here. It's kind of tucked in behind here is the bubble wrap itself. Yeah, I thought I had a better view of it. Anyhow, so we have our steel and we have it going in, and it was like, man, I do not want to try to figure out how to engineer proper thermal breaks for this, because I just don't want to do that. That's just adds a level of expense and complication to residential construction with builders who aren't used to dealing with that I just didn't want to add. So what I came up with is in the crawl space. So here's our bubble wrap room. And then here's our steel that moves through. So that's these elements here, here, and here, and here, and here, that move through underneath our bubble wrap room and are cold. And so what I did is I did spray foam around the steel, and I put a little bit of insulation above it as well. So essentially there's a steel moving through the inside of my crawl space that's cold right now because it's January. And I've tried to, as best I can, to deal with thermal bridging by making that steel kind of part of the thermal outside of the building. And it seems to work, actually. I was a little afraid there'd be maybe condensation lines, there'd be like lines of condensation here as the warm, moist air inside, from boiling pasta or taking showers, hit the cold, the cold surface of the steel, or that I'd be able to walk across the floor and feel the cold steel, but it really hasn't been a problem. No condensation in the crawl space. It seemed, this plan seemed to work. But I was nervous that all the benefit I was doing from using bubble wrap instead of glass, everything we just figured out, that 21,000 BTUs versus 1,300 BTUs just for the wall, I was afraid that I was undoing a good portion of that by having these elements kind of move through. But I think I dealt with that.
Thank you.
And if you want to read more about it, it was written up in Dwell a few months ago. So you can type in my last name, Ermann, and Dwell on Google, and you can find that article. It won an Architizer A+ award also this year. Or if you go to my website, michaelermann.com, you can read a bit about it too. Other questions?
I have a question.
Yeah.
I have written that in the chat, but it's kind of like a related but a different perhaps subject. But like, how do we calculate the temperature in the middle of the wall? And
Temperature in the middle of the wall.
Is it related to area as well? Perhaps not, but
no,
correct?
it's not. That's a good question. And I think I will do 40 minutes of future 40 minutes of competence on that. I will put that in the queue. But here's the short answer. Here's the question answer, because it's probably 30 or 40 minutes to explain properly. If you have an R value, let's make it simple numbers, okay? Let's say you have an R value of total R value of the assembly of 40. And outside you have the delta T between inside and outside is equal to 50 degrees, like we just saw. Now, what you would do is you would look at this more carefully, and in reality, you have drywall, you have insulation, you have sheathing, you have brick. And the question is often like, what is the, I don't mean the question on the exam, I mean the question in life, because there's often a layer here that is vapor impermeable, and the fear is that warm, moist air from inside will build up as condensation on that surface. So the question is, what is the temperature at that surface? And so what we're going to do is we're going to figure out the R value outboard of that surface by taking the brick and the airspace and whatever. And we'll take the R value on the inside of that surface by adding the insulation and the drywall and maybe the sheathing, depending on where that cleave mark is. And let's say that 20% of the insulative value, 20% of the total R value is outboard of point A, this point that we're searching for. The temperature at. So we're trying to figure out the temperature inside the wall, right? And we'll say that 20%, and we'll say that 80% of the R value is inboard of that point. You got me so far? You on board?
Yes.
Okay.
Yes.
So most of our insulation is inside. 4/5 of it is inside. 1/5 of it is outside. When we do that, we know that from a delta T point of view, that if it's 69 degrees inside and 19 degrees outside, like the one we just did, we know that's a delta T of 50. We know that that point A is going to be 80% closer to 19 degrees than it is to 69 degrees. Got it? So it's going to be, so if we have 50 total delta T, we have a delta T between outside and that point of 1/5 of that at 20%. So it's 10 degrees and 40 degrees to the inside. So we can add 10 degrees to 19 or subtract 40 degrees from 69. Let's add 10 to 19, it's easier. It will be 29 degrees. So step one is figure out the total R value. Step two is figure out what percentage of the R value is outside the point versus inside. And then step three is figure out what's the delta T. And step four is figure out, okay, given that 20% is outside that point and 80% is inside, then I know that the delta T, the difference in that 50 degrees, 20% of it is going to be on the outside of point A, and 80% of it is going to be on the inside. I have time for one more question.
Thanks. Just one more. So for this, we would consider for sure the thicknesses for each material, but we wouldn't consider the total area, for example, similar to how you had it with the BTU.
Correct. Correct. But it's when you say thickness, you mean the R value. So there's two different R values given. Sometimes it's per inch, which is a resistivity for a homogeneous material, and sometimes it's per unit, so it could be per CMU for a non-homogeneous material like CMU, where you have air and concrete in the assembly. For drywall, which you'd think would be kind of homogeneous, but the paper is enough different than the drywall itself and the gypsum board that they don't consider it totally a homogeneous material. For Gosh, I'm trying to think of for wood, for concrete, for even brick, for glass, you can do it. For insulation, you can do it per inch. But for building components, carpet, something like carpet, or even paint or something like that, it's usually per application. All right, I have time for one more question.
Hi. I have a condition in a project that I'm doing that we have a really tall cow wall system with glass above.
Mm-hmm.
So so they're 16 feet tall, and then we have to add a structure tube at the 10'6", let's say, height, so we can brace the cow wall to it. Is it better to run the window in front of the structure?
Yes.
Okay.
Literally.
Okay. Good.
Yeah, as much as for all the reasons I just showed you with my structure, like it's
Right.
always better to have. It's always better to have as much as possible inboard of the insulation of the thermal envelope.
Okay. Great. Thank
All
you.
right. Good night. Get licensed.
Thank you. Bye.
Thank you.